Okay, how's everyone doing?
Great.
Okay, awesome. I realize I'm between you and the weekend, so I'll try to keep it, well, not short, but at least try to keep it interesting today. All right. Okay, so this is part 3 of this short course on Radiance Fields. Let's do a quick recap. So this is our course map. We are in part 3 today, which is going to be on 3D Gaussian Splatting. So far, we've talked about an introduction to what radiance fields are, history of radiance fields. In the previous lecture, we talked about neural radiance fields, which is one of the most kind of a turning point in the history, in the short history of radiance field literature in the last few years. And today, we are going to continue this discussion with 3D Gaussian Splatting. Okay, but before we do that, let's do a quick recap of what we've talked about so far. So far we've talked about, in the previous lecture we talked about NERF. So let's do a quick recap of what NERF is, just so that we're all on the same page. First of all, NERF captures radiance fields, and radiance fields themselves are related to the planoptic function or the light field. So what is the light field? The light field represents, in a given volume, it represents at all points in all directions light energy that's traveling through all points in all directions. Roughly speaking, that's what the light field captures. And the planoptic function gives us a relationship between some parameters that represent, let's say, the position and direction at a certain point in space, and maps it to some kind of radiance value, or specifically the integrated radiance value. That's what we get with the light field representation. Okay, and this function can take in many inputs. Typically, we think about position and direction. But we could also think about things like wavelength and material properties and things like that, right? So we're not going to talk about that, but this can contain other things and time as well, right? If you have a dynamic scene. Okay, so that's the planoptic function. A radiance field is similar to the planoptic function, except that instead of storing at each point and direction, instead of storing the integrated radiance, it's actually storing the radiance at that point only, right? So that's the difference between a radiance field and the light field, okay? What that means is that if you're trying to do volume rendering, so what is volume rendering? Volume rendering is the process of taking a radiance field, or it could also be a light field, but if you have a radiance field, the way you would do volume rendering is you would take this scene for which we have the radiance field representation, okay? You would sample rays on a camera. So you need to know something about the camera geometry. You need to know the position of the camera. You need to know the orientation of the camera. If you know that, and from basic camera geometry that we briefly touched upon in the previous lecture, you can form these rays that intersect the scene at certain points. You can then sample points on this ray. We are now looking at a two-dimensional cross-section. So you can sample points on the ray within a certain bounded volume, represented by this blue thing here. And you can sample multiple points along that ray. Okay? So the process of volume rendering takes a radiance field, samples the radiance field at different points along the ray, accumulates all of them using this integral function, and figures out what should be the color of this particular pixel here on the image. Okay, so that's what volume rendering means. You have a radiance field. You have at each point on the radiance field, we get some information about the radiance. You integrate it across the ray. You get the integrated radiance, which is what is observed by the camera here. All right, so that's just a recap of volume rendering. Okay, so NERF is also helping us do volume rendering. The only difference is how the radiance field is stored. Okay, so if we were to do this naively, we can think about representing the radiance field within this box. Maybe we can divide this box into lots of little pieces, like voxels, and then we can store the radiance field value there. But instead of doing that, in NERF, we store the radiance field because the radiance field is a function. Okay, it's a function that takes position, direction, maps it to radiance and density. Okay, so we can represent this function using a neural network, a fully connected neural network. So this neural network takes as input position, direction. There's some additional positional encoding if you want to capture high frequency detail, and it outputs radiance and density. So in practice, this integral equation will become a summation, because when you have this ray and you have lots of different points on this ray, you take discrete steps along the ray. So that, instead of writing a continuous integral function here, you would write it as a summation. So that's how we evaluate this in practice. All right, so that's where we left it in the previous lecture. Any pressing questions before we continue? Yeah.
So basically here we don't use the depth information as of now. So
Sorry, we don't use?
Depth information.
Depth information, no, we don't, no.
So what was the reconstruction that we have discussed in the previous lecture? We have a scale, right?
Up to a scale.
Yeah, with a true value.
No, that doesn't, it's not directly related to the depth. So you can still get a metric reconstruction here. It doesn't have to be up to scale. It depends on, because that is a function of your camera calibration. So when you get the position of the camera, if you get the position in real world units, everything else is going to follow real world units as well.
But when we have to trace a ray, we have to choose certain near and farther points, right?
Yeah.
So that farther point.
But everything is in the coordinate system of the camera. So if the camera is calibrated in the in the real world units, let's say meters, right? Everything is going to be in meters as well.
Yeah, but still, if we don't know the depth information, we cannot get the actual metric coordinate of the feature, right?
No, you don't need depth for this. Because you don't have one camera, you have lots of cameras. And you're shooting rays through all of these different cameras when you do volumetric rendering. And the cameras are already in real world space, let's say. So you know where the cameras are. One camera is here, another camera is 10 meters away, another camera is 15 meters away, right? And you can shoot these rays. You can just use basic trigonometry to figure out what the ray direction should be. And you simply just sample points along that ray.
So only in that case where we exactly know the camera's positions, we can get the metric depth. Otherwise, say for example, if we estimate the camera positions using say call map, under that circumstance,
and at that point it will be up to scale, right? Because when you use something like call map, which we'll talk about at the end of lecture today, the reconstruction that you get is up to scale. So at that point it will be up to scale. But if we are assuming here that the cameras are all, if they are in real world coordinates, then everything is metric. All right. Okay. Just a quick recap of some of the results from NERF as well, right? So this is the kind of novel view synthesis results that we get. So although the way this image was, this reconstruction was produced is we took a bunch of pictures, but then this video shows you viewpoints that were not taken during training the NERF model. Okay, so you're able to generalize across new views, and this process is called novel view synthesis. When we are creating these new views of the scene. All right, so today we are going to focus on 3D Gaussian splatting, which is a newer technique for doing volumetric rendering using Radiance Fields. It's a natural progression of NERF, but then here we throw out the neural network completely, and we'll discuss how this is done in the next few slides. Okay, at this point I should thank lots of my colleagues who helped with many of these slides, so you'll see some of their work there. Okay, so let's recap. What is the novel view synthesis problem? In computer vision, when we talk about novel view synthesis, what we mean is that we image a scene at a certain number of positions, camera positions. So let's say you have this room, you'd like to create a representation of this room, for example, as a radiance field. Let's say you take 100 pictures. So you go around this room, take 100 pictures, right? But let's say you never took a picture from somewhere up here on the stage, okay? So if you want to see how this scene looks like from the stage, although you don't have any pictures, but you have a 3D reconstruction of the scene or a radiance field of the scene, right? So then you can do that using techniques that we've talked about. So this process is called novel view synthesis. Novel meaning views that you haven't seen before. You're synthesizing views that you haven't seen before, okay? And usually this is visualized as some kind of a fly-through in your scene, right? So for example, this is a NERF scene that has been created using maybe 100 images, but then we are now taking like a continuous sample in a circle, right? No such image was taken during training process, but you can still synthesize those. That's why we call this novel view synthesis. I skipped through the animations. Okay. So why is novel view synthesis important? It's important in a lot of different domains. It's important, for example, in mixed reality or virtual reality, where you may want to exactly replicate the scene in VR headset so that you can immersively view the scene, right? And by the way, this is something that's available already. So if you have access to like one of the Meta Quest headsets, there are some demos in there that actually use Radiance Fields to recreate environments that you haven't been before. And that's actually quite immersive. And because you can do novel view synthesis, when you're wearing a VR headset, the headset can track your head's position. And if you haven't been on stage, in virtual reality, you can actually come onto stage. The VR headset will track your position, and then it'll show you how things look like, right? So in applications like this is pretty useful. This is also useful, as we've seen in the first lecture, for things like Street View and 3D view, map view in Google Maps, and so on and so forth, right? So lots of different applications. Okay, and so far we've talked about NERF, which essentially captures the scene, the radiance field of the scene, and encodes it using a neural network. So if you want to figure out what is, how does a novel view look like, you're going to shoot rays, you're going to sample points. At any point, you have a point and a direction along the ray. You feed that into your neural network, you get the RGB and density, right? And then you do volumetric rendering. You do the integral equation, you do the summation, and you get the color, right? So that's how we've been treating the problem so far. So the representation of the world is actually a neural network. The neural network tells us how the radiance field looks like, right? That's what we've seen so far. This is what we call an implicit representation. So why do we call this an implicit representation? The information about the 3D world, the radiance field of the 3D world, is not stored explicitly. It's not stored in like a table that says, okay, if I'm at this position, I should have this radiance value, right? In other words, you can think about voxelizing the space. You can divide the space into a uniform grid, label each grid point as a voxel, and store the radiance value. So that would be an explicit representation. So you're explicitly dividing the whole space into lots of grid cells and then storing the values at that position, right? Like a big 3D table, right? Whereas here, it's not an explicit representation, it's an implicit representation. So in order to get the value at a certain point, you need to ask the neural network. It's implicitly stored inside the neural network, right? So that's what we call an implicit representation. So NERF is an example of an implicit representation. All neural fields, I'm not talking about neural radiance fields, just neural fields in general, are also examples of implicit representations. They're capturing the information implicitly through the weights of a neural network. Okay? So that's NERF. Now, the problem with implicit representations, and even some explicit representation, but specifically with NERF, is that every time you need to figure out a novel view, you need to shoot a ray, you need to select samples along the ray, and for each sample location, you need to query the neural network. So if you have 100 samples, you need to do 100 forward passes of your neural network, right? So it's 100 evaluations of your neural network. And neural networks are pretty big. This is going to have millions of parameters, right? So when you have millions of parameters, doing a forward pass of that can be quite expensive, right? So that's one issue. So that's not very suitable for volumetric rendering. So imagine if you have a VR headset and you'd like to render a radiance field in the VR headset, it has to happen in real time. It has to happen at 60 frames per second at the very minimum, right? So NERF is too slow for that, right? We want to have something like this, where we can actually see the scene from any perspective that we like. And we want to do this in real time, right? At more than 60 frames per second. So how do we do that? NERF doesn't allow us to do that because of this very expensive evaluation process for every single point along the ray. Okay? So that's not suitable. I mean, I won't talk much about this, but there's been a lot of work on trying to make NERF faster. I think a good example of that is a paper called Instant NGP, Instant Neural Graphics Primitives. What they do is they still have something that resembles a NERF, but then they also have like a hash table that makes lookups very efficient. I won't go into the details here, but essentially this is one way of making NERF faster. So you can go down this route, right? Try to make these neural network evaluations much faster so that even though you have to evaluate the neural network many, many times, it's still very efficient, right? So that's one way in which you can solve this problem. But what we are going to talk about today, 3D Gaussian splatting, is another way of solving the same problem. 3D Gaussian splatting is what is known as an explicit representation. Okay, so how does that work? Let's say you have the Lego scene, the Lego, this famous scene from the Nerf paper, right? Now, in the original Nerf work, the scene is represented as a neural network, implicitly as a neural network. So you have to query the neural network at certain positions to figure out what the radiance field value is, radiance value is at that point. Instead, what we're going to do here is we're going to have Gaussian functions that are physically located at certain points on the scene. So for example, the floor part of the scene, you would have a bunch of yellow Gaussian functions. And I'll talk about what properties these Gaussian functions have in a moment, right? The wheels of this object have a lot of black colored Gaussians, right? So when I say Gaussian function, this is like literally a Gaussian function as we would, as you all probably studied in like math and physics, right? It's a Gaussian, it's not a distribution, but we are talking about the Gaussian function, right? And it has a very specific form. It has infinite support, so the function never ends, right? It goes down from minus infinity to infinity, right? And here we are actually looking at, these are not one-dimensional Gaussian functions, but you're looking at Gaussian functions in 3D, right? So they have an XYZ position, and they have some kind of a covariance matrix. So if you were to take this, what we are visualizing here, these functions are infinite bounded, right? But what we're visualizing here is an isosurface of this Gaussian function. So we are taking the Gaussian function values at a certain standard deviation or a certain covariance value, right? So that can be like, okay, standard deviation of 1. So where does the Gaussian function have value of 1? Does it evaluate to a value of 1? We draw a surface around it. And it turns out that that surface is an ellipsoid for a Gaussian function. Okay, and that's what we are visualizing here. So what we are doing, for an intuitive way to think about this is you take the scene and take a lot of ellipsoids that have certain properties and put those ellipsoids in the scene. So the ellipsoids become proxies for modeling the scene. Okay, that's what we've done. And because we now have these ellipsoids that we are putting in different parts of the scene, this becomes an explicit representation. So if you want to know what is the radiance at a certain value, you find the closest Gaussian function or the closest ellipsoid, read through some of its properties, and that will tell you something about what the radiance at that point is. Okay? So it's different from a neural network where you have to do this forward pass of that neural network. Right? So here you have this explicit ellipsoids that's just sitting there, and it tells you something about the radiance value.
So when is it an ellipsoid? Which value?
Ellipsoid is when it's a contour of the Gaussian function.
When the value is standard deviation is what?
No, you can find different contours. Think about contours. So what are contours? You have a map that represents height, right? So contour line at a height of 100 meters, contour line at a height of 200 meters, and so on and so forth, right? So we are visualizing these Gaussian functions exactly like that. So when you see this ellipsoid, it's a contour line at a standard deviation of 1. But you can also have contour lines at standard deviation 2, 3, 4, and so on and so forth. Yeah.
So can we think of this as a Gaussian mixture model of several 3D Gaussians, and then we are sampling at specific points to get values?
Yeah, you can think of it like that. In fact, there's lots of similarities, except that in a Gaussian mixture model, you linearly combine all the Gaussians, but here the combination is using something known as alpha blending. We'll talk about that in a bit, right? So it's not exactly a Gaussian mixture model, but it's very, very similar.
Actually, sir, why only Gaussian? Because at the middle the maximum value, but afterwards it decays very fastly. So why we are using this Gaussian?
Oh, so we don't actually care about the value of how we don't actually care about the value of the Gaussian function evaluation, right? Like we simply want some primitive that stores some information about the appearance. So we're kind of using this as just like some primitive. Like instead of a point, you have a point with some function around it that tells you how far away you are from it, right? So it doesn't really matter what that function evaluates to. And it turns out the second reason is Gaussians tend to have very nice properties. For example, if you take a Gaussian function, you can differentiate it, you get another Gaussian function. Take two Gaussian functions, multiply it, you get another Gaussian function, right? So Gaussians have some very, very nice properties that makes them differentiable and so on, right? So that's why we use Gaussian functions. Yeah.
You said we can find the closest ellipsoid to what?
Sorry, can you repeat this question again?
You said to find the closest ellipsoid.
Uh-huh. Sorry, I didn't get the question.
What are we finding the closest ellipsoid to? Like a ray or?
No. What I meant there was in a neural radiance field, the input to the neural radiance field is an XYZ position and a direction.
Yeah.
And the radiance field tells you what the radiance value is, right? But here, you don't have that neural network. So, if you wanted to find what the radiance is at this value, you would find the closest Gaussian function. So when I say ellipsoid, what I really mean is a Gaussian function, right? And then you check the properties of that Gaussian function, and that'll tell you what the radiance there is.
But the way you say that that's the function you need to check is through what mechanism?
Nearest neighbor, like what's the closest to you?
To what?
To wherever you want to evaluate, so that XYZ position or direction.
And we determine that from the
From the radius. We'll get to that in a moment, but that's how we determine that. Okay, does it make sense so far?
Yes.
Everyone with me? Okay, good. All right. So what properties do these Gaussian functions have? So each one is a Gaussian function. It's actually not a distribution. I would call this a function, right? This is a one-dimensional Gaussian function. But what we have here is, we have functions in 3 dimensions, right? So that would be quite different, okay? All right. Now, besides the Gaussian distribution itself, for the Gaussian distribution, we have some properties. So that's the position. So that's the center of the Gaussian function. That can be anywhere in the scene. Usually, it's co-located with the part of the scene that represents. We also have rotation and scale. Now, in a Gaussian function, rotation and scale is represented using the covariance matrix that describes the Gaussian function. Okay, so that would capture rotation and scale of that Gaussian function. Additionally, we have 2 other things. So we have opacity, which is how transparent a Gaussian function should be. So as we discussed last time, if you have smoke or fog, that is transparent, right? Like some light passes through it, right? So you want to model those things as well. So you have opacity, and then you have the color. Just like you have in NERF, you have a color. Color is a proxy for the radiance. Okay, so these are all the properties that every Gaussian function has. So in addition to its basic properties, so position, scale, orientation, right? It also has the additional opacity and color. Yeah.
Color as a proxy for radiance means it's different for different angles, or it is same for?
We will get to that in a few slides. Yeah. Okay. All right. So that's how we're going to model it. Now, once we built this, so our goal is to build this, this structure. So this mixture of Gaussians, if you will, right? So we want to build this mixture of Gaussians so that using some rasterization process, which we will talk about, if you take all these Gaussians, follow this rasterization process, similar to volumetric rendering, we should get an image that looks reasonable. Okay, so that is our goal. So we want to go from here to the images. And again, that's exactly the same as the NERF setting. Right? All that we've changed is that the representation is not a neural network anymore. It's just this explicit set of Gaussians that we built. So the task then becomes not training a neural network, but figuring out the properties of all of these Gaussians. If you find the right combination of these Gaussians with the right properties, when you do the rasterization, you're going to get images that look reasonable. So given multiple views of the scene, we'd like to optimize for these parameters, build this 3D Gaussian, people refer to this as a 3D Gaussian splat. So if you have this splat, then you can get the image that you want to get. You can get the novel views. Okay. All right, so 3D Gaussian splatting is popular because it's fast. It's an explicit representation, so it gives you some sense of the geometry of the scene, the shape of the scene. And again, going back to the first lecture, right? Like we really care about Radiance fields capture two things: appearance and geometry, right? And Gaussian splats do that too, right? And most importantly, they're very fast, especially during rendering time. So if you're trying to do this, implement this in a VR headset, you can actually implement 3D Gaussian splatting. Actually, many VR headsets already do that, and you can do the novel view synthesis at over 90 frames per second or more. So that's very helpful. All right. Besides this, 3D Gaussian splatting is also very popular for a variety of other applications. Things like editing. So you want to change captured scenes, right? You can do something like that with Gaussian splats. You can model humans, which we will talk about on Monday, and then you can also do generative models, right? So you can, just like you have generative image models that produce images from text descriptions, you can build generative models that can produce 3D scenes from text descriptions, right? So those kinds of things are supported by 3D Gaussian splatting. Yeah.
Sir, in the previous slide, there was term mentioned PSNR.
Yes.
What is it?
Okay, so I will not talk about this, but maybe I should have. PSNR stands for, it's the signal to noise ratio, as we would measure in signal processing, right? And that's a measure of how good the image quality is, right? So it's exactly the same as what we would use in signal processing.
Is there any difference in resolution when we compare to NURF and 3D Gaussian splats?
3D Gaussian splats usually can operate at higher resolutions because they're faster to train, and you can do like 4K images, 6K images, 8K images.
And is there any difference of space? Like how much space do NURF consume on a memory and 3D Gaussian splats?
Yeah, good question. So because we are storing all of this explicitly, and usually, I mean, this question comes up sometimes, right? Like, how many Gaussians do we need to model a scene? Right? If your scene is really complicated, oftentimes you need hundreds of thousands, if not millions of Gaussians. Right? So that means million times how many parameters you have. You have to store that many floating point values. Right? So it can get pretty memory intensive.
And in case of dynamic scenes, like some moving scenes, so does NURF are better to use in dynamic scenes especially, or Gaussian splat?
The vanilla versions of both of these models do not model dynamic scenes, right?
Okay.
So there are improvements on top that model dynamic scenes. They have different goals. Some are memory efficient, some are not. But as we are going to discuss it today, it does not model dynamic scenes, only for static scenes. But you're right. If you have a dynamic scene, then every frame needs to have this many things. On the other hand, a neural network is very compact. So it's much more compact than having all of these parameters. So NURF is often very small compared to 3D Gaussian splatting scene. Yeah.
So there's something which compares with training time as well in your previous slide.
Yes.
What exactly is this? Is this something like the test time training wherein we get a cap?
Yeah. So the terminology here is a bit misleading because Gaussian splatting followed NURF. And in NURF, you have a neural network, and therefore you train a neural network, right?
Yes.
But with the Gaussian splat, there is no real training. You're just optimizing for the positions and orientations and other parameters of the Gaussian functions, right? So I think a right way to describe it is optimization or fitting, right? But people colloquially call it training, right? Yeah. All right. Okay, so yeah, we've talked quite a bit about NURF versus 3D Gaussian, so we will skip through that. Okay, what we're going to do maybe in the next 15 minutes or so is we're going to look at every component of 3D Gaussian splatting. And we're going to try to understand how it works. Okay? And there's lots of similarities to NURF, but there's also lots of differences, right? And we're going to try to highlight what the similarities and differences are. Okay, so roughly speaking, the way 3D Gaussian splatting works is that you start off with some initialization for the position and properties of the 3D Gaussian functions. And then you have a bunch of images of the scene. And those images provide supervision or provide signals that tell us how we should change the initial parameters of the 3D Gaussians so that they all find configurations in which when we do the rasterization, we get an image that is very similar to the ground truth image. Okay? So at a high level, that's really what's happening here. But then there's a lot of details that we need to talk about. Okay. I'm going to try to give some intuitive understanding here of the rasterization process as well, right? So in NURF, it was pretty straightforward. You shoot rays, you sample the rays at different points, query the neural network, get the value, accumulate everything using this integral function, right? So that's pretty straightforward. But here it's a little bit more complicated because you have these functions, right? So you need to evaluate the function to figure out what's going on. So one way to think about this is think about each of these Gaussian functions as some kind of a snowball. So remember the ellipsoid that I talked about. So you have different ellipsoid that represents a contour line in a Gaussian function. So think of these snowballs as these ellipsoids, okay? And then the rasterization process, so going from here to here, is using something known as splatting, okay? So splatting, very, very simply, is to take these snowballs and to just throw it at some kind of a wall, a planar surface, okay? What happens when you take a snowball and throw it at a wall? It splatters, so it becomes two-dimensional, right? So the rasterization process that we're going to use to go from the 3D Gaussians to the image is known as splatting. That's actually why we call this 3D Gaussian splatting, okay? We take the 3D Gaussian functions and we throw them all at an image, okay? And it turns out that ellipsoids, or if you take the contour line of an ellipsoid, have very nice properties that make this process analytical. What I mean by that is we know how to write the equation of an ellipsoid. We'll talk about that in the next slide. If you know the camera parameters, where the camera is, and you know the camera geometry, you can take that ellipsoid equation and directly get the ellipse equation that is a projection of the ellipsoid. So this is, again, going back to some geometry here. So if you have a three-dimensional ellipsoid, a two-dimensional projection of a three-dimensional ellipsoid is an ellipse. Okay? And you can get the exact equations of the, if you know the ellipsoid, if you know the camera, you can figure out what the ellipse equation should be. Okay? So ellipse and ellipsoid. So ellipse is in 2D, ellipsoid is in 3D. Okay? So that makes this whole process very, very efficient. You can write this down analytically. So you can write down an equation that tells you exactly what should be the ellipse equation if you know the ellipsoid equation. Okay, so that's the advantage. Now, the other advantage is that we put these 3D Gaussians only where there is some object. So remember, when we talked about Radiance Fields, we said that, we don't know what is in this part of space. I mean, we know that it's air, but air can also like scatter and so on. But here we're going to simplify the whole thing. We're going to say, I put 3D Gaussians only where there are more or less opaque objects. Okay, so I would put 3D Gaussians near the ear of this bunny, but I wouldn't put any Gaussians elsewhere. Right? So what that means is we also get some kind of sparsity in the representation. So we no longer have to sample every single point along the ray. We simply shoot a ray, find all Gaussians that are within a nearest, close to that ray, within some threshold of that ray, right? And then we just take those Gaussians, do the splatting, that will tell us where they splat, and then we do some kind of ordering, and then we take all the Gaussian parameters and figure out what the color should be. Okay? So it's far more efficient than NERF. We no longer have to do these hundreds of evaluations. Instead, we just have to do maybe like tens of evaluations, right? And everything is analytical. So you don't have to query a neural network. You just simply know what the equation is. You can just write down the equation for the whole thing. Right? And the other nice thing with 3D Gaussian functions is that they are differentiable. It's very easy to analytically find the derivatives of Gaussian functions, right? So all that makes it easy to do the optimization, because for doing optimization, we need to find gradients, right? And we can find analytical gradients because everything is a Gaussian function. All right, so that's just to motivate why Gaussian functions are good in this context. Okay, the term splatting is kind of used casually these days. So you call a scene that is captured using 3D Gaussian splatting as a 3D Gaussian splat. But it's somewhat misleading because the word splatting actually just means to throw the snowball at the wall, right? So that's what splatting means in traditional computer graphics. In fact, one of the first papers to talk about this is actually a thesis by Westover from '91, right? So which is where this whole splatting process for Gaussian functions was introduced, right? So this is a very old concept. It's not an entirely new concept. Okay, all right. So let's walk through the steps in building a 3D Gaussian splat, okay? So the first step is we need to initialize these 3D Gaussians at reasonable positions, okay? Now, if you've taken an optimization class, you know that if you have a non-convex function that you're trying to optimize over, initialization is very important. If you don't initialize it well, you get stuck in local optima, right? So you want to avoid that. So how do you avoid that? We're going to put Gaussians in space that are roughly in the same position as things in the world. And the way we do that is using some classical computer vision techniques, specifically structure from motion. Okay. If you haven't taken a computer vision class, it's okay. But roughly speaking, what structure from motion gives you is if you have a bunch of cameras, it tells you where the cameras are, and it also gives you a very sparse 3D reconstruction of the scene, which is represented as a point cloud. So these are just a bunch of points in the world. Okay? For every point, you have an XYZ position. So that's what structure from motion gives you. Okay? And you can do this using popular packages like Colmap. So Colmap implements structure from motion.
And number of points in the cloud is related to?
Well, it's related to the number of matches that you have. We will have to dive into the details of structure from motion to understand that. But essentially what happens with structure from motion is it takes all these images, finds what are known as key points or interest points, and then matches those interest points across the views. So the number of points that you get is a function of how many interest points you're able to detect. Okay. All right. So what we're going to do is we're going to take this point cloud that we get from structure from motion, and at each point that we get in SFM, we put a Gaussian function there. So we set the Gaussian function position, XYZ position, to be the same as the points that we have in the 3D point cloud. Okay, so we take this point cloud, put a Gaussian at every position where we have a point. That's how we are going to initialize the whole thing. Okay, so pretty straightforward. We take an off-the-shelf method, get a 3D point cloud, put Gaussians at every single point. All right. So the mean is set from this initialization. So the initial mean, right? We're going to optimize it, but the initial position of the Gaussian function is decided by this point cloud, the structure from motion point cloud. We're going to set the covariance of all the Gaussians to just be isotropic, meaning they're not ellipsoids, but they are spheres, right? A sphere is a special case of an ellipsoid, where the covariance matrix is all the same. Along all directions are the same. Okay, so we initialize it like that. And we also choose some initialization values for all the other parameters, like opacity, color, and so on. So you could choose to start from all gray colors or things like that, right? So you just start with some reasonable initialization. Okay. There's also, the way we model color is a little bit different, so we'll talk about that next. Yeah, maybe I should have flashed this equation at the very beginning. So this is how we would represent a Gaussian function, right? So g of x, represented by this exponential. X goes in here, it's kind of like a quadratic function, and then you have a covariance matrix in there. Right? So that's how we represent a Gaussian function, okay? Now the equation of an ellipsoid is the whole, it's not the whole thing, but it's just without the exponentiation. So if you have an ellipsoid, that's the contour line, that is simply x transpose sigma inverse x, right? That's the equation of an ellipsoid. So that's how a Gaussian function and an ellipsoid are connected. Okay. Now, what we're going to do is we have, in our 3D Gaussian splat, we have our Gaussian function, we have the position, we have all the other properties. We also have opacity, which is represented using this small sigma over here. Right? That's an additional property that the Gaussian functions don't have. Right? So that's, you can think of this as a weighing function that tells you how much each Gaussian should be weighed when we do this integration at the end. Okay, so we have that here as well.
So the second function is the point cloud.
No, the second function is our 3D Gaussian splat. So what we actually use at the end.
Fi finally outputted is the value of?
It is you can think of this as the radiance. Okay? It's an approximation of the radiance. All right. Okay, I'm running a little bit behind, so I'll skip through this, except to say that 3D Gaussians have some very nice properties that makes it desirable. So it's continuous, differentiable, right? So all that really helps when you're trying to do optimization, right? So that those are all advantageous properties. Okay, so what we're going to do during optimization is we're going to try to figure out what should be the covariance. We initially started off with a sphere. So the covariance matrix, all the radii are the same. right? But we want to figure out what is the right scale. We want to figure out what is the right covariance matrix. So we want to optimize for all of that. And to facilitate optimization, we represent the covariance matrix as this product of rotation matrices and scale matrices. Okay, so it's just R is the rotation matrix, S is the scale matrix. You can write the covariance matrix. If you know the rotation and scale, you can figure out what the covariance matrix is. Okay, so that's just the way we optimize for it. And scale is just 3 parameters. So scale along X, Y, Z. Rotation is, you can think of this as like 3 radii, right? You can have that. Sorry, the scale tells you the radii, so along each dimension, and the rotation tells you what should be the orientation of the ellipsoid. Okay, this just makes it easy for optimization. You have 3 parameters for scale, 3 parameters for rotation. So you have 6 parameters in total that determine what the covariance matrix should be. Okay. All right. So the last step is splatting. So once you've optimized for the parameters of the Gaussians, you have to do the splatting. And as we discussed, splatting, Gaussians have very nice properties. So you can write like an analytical thing that tells you how this 3D Gaussian projects to a 2D ellipse. Right? So 3D ellipsoid projects to a 2D ellipse, right? And you can find the equation of this ellipse analytically. So if you know the 3D Gaussian, you know the camera, you can figure out what the ellipse should be. Okay? So that's pretty straightforward. All right. Yeah, I will skip this. Okay, let's talk about the next step after we do the splatting. Now we shoot a ray. We figure out what are all the Gaussians that are near that ray, just like we do in volumetric rendering, right? We do the splatting, so each Gaussian projects onto the image, but they all project one on top of each other because they're all along the same ray, right? So we need to blend them somehow, okay? In order to do this, there's some details that I'm skipping through, but essentially you first figure out some kind of order. So you figure out what's the closest Gaussian, what's the furthest away Gaussian. This is important because what's behind the wall, I don't know, right? So if I start blending stuff from the back to the front, I will kind of see what's outside first, then I will see what's inside. That's not what I want, right? So I want to blend from close to the camera to far away, right? So I do some kind of sorting of the Gaussians based on distance. Okay, so this Gaussian is first, second, third, fourth, and so on and so forth. Okay, so I do this sorting. And once we've sorted all the Gaussians based on distance, we can then blend all of them together. So remember the opacity term that we talked about, so we can take that into account. And then the final blending equation, where is the blending equation? I think I have it in a few slides later. But there is an equation that tells you how you can blend all the Gaussians together. And that gives you a color for a pixel. Okay, so that's similar to what we get with a NERF. Right? So you have array, sample points, accumulate all of them, get a color. Same thing here.
Would it be more useful if we splat all the Gaussians instead of looking at an array? Because we need to finally render the whole frame.
No, but cameras don't look at the whole thing, right? Cameras have a frustum, like a view, right? So they only sample a subset of the light field.
In that case, we can only take all the Gaussians in that frustum and splat them all.
That's what we do, yeah. We don't take all of them. I mean, it's also more efficient to only splat stuff that you see. Right? You don't have to splat every other Gaussian, right? Yeah.
The Gaussians have infinite support, so we don't project all of them, or we just pick them.
We are actually not projecting it. Okay, so I think it's easier to think about this as projecting an ellipsoid, right? So when you project an ellipsoid, you get a 2D ellipse. That 2D ellipse is also a Gaussian function. So it has infinite support in your image.
But like which Gaussians to pick, because all the Gaussians have infinite support. So when we shoot a ray,
Oh, you just find the nearest distance to the centroid of the Gaussian.
and we have some threshold that
Yeah, you set a threshold. You say that if the centroid of the Gaussian is close to the ray, under some threshold, then I'll pick that Gaussian. Yeah.
The opacity is constant, or
It's also optimized. So you optimize for the opacity.
for a given Gaussian, the opacity also goes down as you go farther away from the.
No, the opacity is independent of the camera, right? So in your radiance field that you learn, different Gaussians have an optimized opacity.
For a given Gaussian,
Uh-huh.
opacity is a single number.
It's a single number after you optimize it, yes. All right. Okay, so the advantage here is that you don't have to query the MLP every single time. You just find all the Gaussians that are nearby, splat them, figure out what the value of the blended whole thing should be. Okay, so it's much more efficient than NERF doing this kind of splatting. It's sparser, it's also analytical, so you can compute these things very, very easily. All right. One other detail here is how we represent color. Okay. So far, we've assumed that color is like an RGB, so you can take all the RGB values, blend them together, right? So each Gaussian has only one RGB color. But the problem is, points in the world can have different colors depending on where we are looking at it. Okay, so a good example of this is any surface that's shiny. Okay, so you take like a display. I'm trying to find a shiny object here. Yeah, water bottle. Let's take water bottle, right? So this bottle, if you look at it from here, has a certain color. If you look at it from somewhere else, it has a different color, right? The same position has a different color, right? So what this means is that things are view dependent. How things look depend on where you view them from, right? So that's something that we might often want to capture, right? So how do you do that? It turns out that we can use something known as spherical harmonics to capture view dependent color. So what are spherical harmonics? They were originally invented by mathematicians and physicists to model something in quantum mechanics, which I don't know details about. But in graphics and in computer vision, we use this to represent view-dependent color. So what color do I see if I look at an object with the same point on the object from different views? Okay? And very roughly speaking, spherical harmonics can be thought of as Fourier series or Fourier expansion in the spherical domain. Okay, so what is the Fourier series expansion or Fourier transform? So you have a complicated function. You can write that complicated function as a weighted sum of sines and cosines. So that's what Fourier decomposition theorem says, right? Similarly, there is an equivalent for that in spherical space, where what you have is, if you have a function that is on a sphere, that is defined on a sphere, think of something like a gravitational field, right? That field or that function can be described as a linear combination or some combination of basis functions. Okay, and these basis functions are called spherical harmonics. Okay, so you have different harmonics meaning different bases, right? So you have level 1, level 2, degree 1, degree 2, and so on and so forth, right? So you can actually use this kind of spherical harmonics to represent functions that are defined over a sphere. Why over a sphere? Viewing a point from different direction can be thought of as a spherical function. So every direction you view this from, it looks slightly different, right? So that's why we model this using a sphere. Okay, so yeah, so what we actually do in 3D Gaussian splatting is we model view-dependent color using 48 parameters. So we're going to use fourth order spherical harmonics. So we're going to use fourth order harmonics. So in total, we have 48 parameters that represent view-dependent color. So depending on where you're viewing a point, it'll give you a different color, essentially. Okay? All right.
Slightly off topic.
Yeah.
Can this spherical harmonics also be used in the regular computer vision instead of just dealing with RGB for whatever task?
Yeah, I mean, if you have tasks that require viewing from different, if you have a spherical function that you want to model, then it makes sense to use spherical harmonics. So it's actually already used in computer graphics. So if you do like, it's often used to capture the distribution of light in a scene, right? So you build something known as a BRDF, bidirectional reflectance distribution function, and you can use a spherical harmonics to represent that. So it's been used in computer graphics for like decades already. So we're now using that in the context of Radiance Fields as well.
Every Gaussian we have this spherical.
For every Gaussian, you have a spherical function that is described by the spherical harmonics or the spherical harmonic coefficients. Not to be confused with the Gaussian function itself, right?
Yes.
So this is another spherical function on top of it. Yes.
48 parameters for an entire point cloud seems like a lot.
No, it's not 48 parameters for an entire point cloud. It's 48 parameters per Gaussian.
Yes,
Yeah.
per point in a point cloud.
Correct, yeah.
Isn't that like huge?
Yeah, but it seems to work, so we do it. Yeah. And it's still faster than NERF. Yeah. Okay, so this is the blending equation. Okay, so you have a bunch of Gaussians. You can blend the color of all of these Gaussians using this blending equation. Let's see. Yeah, so each Gaussian has the opacity, and then you can evaluate the Gaussian function to get the radiance value. So the RGB value, which is view dependent, right? So you can get that color, and you can get the opacity through that. Okay, so let's see look at a summary of creating all the Gaussians, right? So we have, as you said, lots of parameters, right? So these are all the parameters that you have for every Gaussian, okay? And you have all of these parameters for millions of Gaussians usually in scenes, right? So you have 3 parameters for the position, 3 for scale. We are using 4 for rotation, probably like a quaternion representation, and then 48 for spherical harmonics, and then finally 1 for opacity. Okay, so these are all the parameters that we are optimizing over. Multiply this with a million, right? So that's how many parameters we are optimizing. Sorry, this is the blending equation. Okay, so the color at any pixel is a combination of the opacity, the color at a certain Gaussian, and then some kind of a blending function. So this blending function is basically the opacity of everything else, all the other Gaussians that you have when you find the nearest Gaussians along the way. Right? So this is the blending function that we're going to use to blend all the Gaussians together. So the C that you get is the color of that pixel.
Oh, the opacity here is a vector.
No, it is not a vector, it's a scalar.
The alpha I, we're talking about multiple alphas.
I here represents the selected Gaussian along array. J represents the non-selected Gaussians along array.
But what about alpha?
Alpha corresponds to I.
No. I mean, we have alpha I and we also have the alpha J's, right?
Correct. So that's the alphas of all the other Gaussians. Alpha J represents the alphas of all the other
Bunch
Gaussians.
of scalars. It's not a vector.
No, but one Gaussian has only one scale.
Yeah.
Right. But you have a lot of Gaussians.
Okay.
Right. Yeah.
When you're taking the opacity of the non-selected Gaussians, we're considering only the I-1 of the Gaussians. So
Yeah, so we'd have to dive into how blending is done. So blending, I could probably teach a whole lecture on blending. Blending is very complicated, but it turns out that there are different ways of blending, and this is one way of doing blending. Where if you have, I think a simple way of thinking about it is you have 2 images and you want to merge them into a single image. You can take 25% of one image, 75% of the other image, right? So if you say my opacity for the first image is 25, the other portion of it is 1 minus 25, which is 75. Right? That's how you combine this.
No, I'm asking why you're considering only like I.
Because the opacities have to sum up to 1. But yeah, we can take this offline. I can give you some references about this. Yeah.
Modeling one way and the light that gets blocked by all the Gaussians upfront is what they.
Right. This blending function captures. Yeah. Okay, the final thing is how do we optimize, what is the function that we optimize for when we optimize the Gaussian? So that's this loss function here. It's a very simple L1 loss, so we want to match the color that we get to the ground truth color, and there's also an additional structural similarity loss, which is the second term that you have there. Right? So you use this during optimization. We typically just use very simple optimizers, gradient descent, stochastic gradient descent. Right? That's what we use.
What's it? BS?
So yeah, SSIM is a structural similarity metric, right? So it's a way to figure out how similar 2 images are, or parts of 2 images are, right? So we want to make sure that the ground truth and the image that we generate using Gaussian splatting, they look similar, right? So we're using that as a measure of how similar they are.
Yeah, but that would be the natural images. Does this extra D say something else? It says
Oh, DSSIM. Good question. I don't know.
It's just a difference. Single is a similarity measure. You want them to like loss. You want them to look like loss. It's 1 minus.
Oh, I see. Okay. But why does it say DSSIM? I'm not sure. Difference. I see. Okay.
Distortion.
Oh, okay. But I can check this for you. All right. Yeah, I'm almost out of time. So let me wrap up with a couple of more things. There are some details here. There's lots of additional details that if you're looking to implement this yourself, you have to take this into account. One such detail is, we start off with a certain set of Gaussians, but then we don't keep the same set of Gaussians. We can merge Gaussians if we don't need them. We can also split Gaussians when we need them, right? So those are some additional details. So you can, let's say you have a Gaussian that can't fully represent a shape, then you would clone the Gaussian so that you can more accurately capture the entire shape, right? There can also be a case where your Gaussian is too big, that it can't capture the complexities of your scene, in which case you have to split the Gaussians so that you get more Gaussians and then you can more accurately represent the scene, right? So there's merging and cloning and splitting strategies that we need to adopt. Okay, let's look at some results. And rather than showing you videos, I am going to show you a live view just to demonstrate that you can do this in real time. Okay, so if you go to gsplat.tech, they have a bunch of Gaussian splat scenes. Let's take this one. It's a hilltop small church, right? And what it's doing is it's actually loading all the parameters of my Gaussian functions, right? So millions of parameters that we talked about, right? It's loading. As you can see, it's about 100 megabytes, not too bad, right? And then you get something that looks like this, which is now fully interactive. So I'm moving this with my mouse pointer here, right? This is a fully interactive scene where you can look at the scene from any possible perspective. You can zoom in, you can go into the details. And as you zoom in, you start to see these kind of little Gaussians here, right? So all these pieces that you see are Gaussian functions. And these are like sliver Gaussians. So they have covariance matrices that are very elongated, right? So you kind of see that here. But you can see that as you zoom out, you get a much really high quality scene representation, right? So feel free to go to this website if you want to take a look at more such scenes. Maybe let's look at one more. Why don't we look at a shoe, right? So one of the potential applications of this is trying to sell products online, right? Let's say you're trying to sell a shoe, right? People would like to look at it from different perspectives. So here's a shoe, and you can look at this from all of the different perspectives, right? You don't see the sole of the shoe or the bottom of the shoe because there's no camera viewing that bottom, right? So you can't really see that.
So when we're moving the position, right? Basically, it's like we're trying to place a virtual camera there.
Yeah.
But for that particular camera, on the fly, we are trying to calculate the position orientation.
Yeah. So what's happening here? Every time I move my mouse pointer, is we take the million, or not the million Gaussians. We're shooting rays.
Yes.
A lot of rays. We're finding the nearest Gaussians, splatting them, ordering them. Then we're doing the blending, and then we get the color, right? All of that is happening for every single pixel that you see here in real time.
But there is no SFM involved when we move the position.
This is an optimized Gaussian splat, right? So you already know where the Gaussians are, right? We are not trying to train or we are not trying to optimize the Gaussian splat.
Okay.
We are only viewing the Gaussian splat. So that's the difference.
So this would be like a point process point cloud.
This is not a point cloud. You're still looking at a radiance field.
Okay.
Right? You're looking at a radiance field from various different perspectives,
Okay.
right? But you're not actually training or optimizing the parameters of the Gaussian functions. Those are fixed, right? You're merely just viewing it, how it looks now, right? And because this has been trained well or optimized well, it looks very realistic. Right? And that's literally what's happening. All these million parameters are being projected, alpha blended, right? All of that is happening in real time across all of these pixels on my tiny little laptop here, right? So that tells you something about how fast these methods are. Okay, the last thing for today is if you are still interested in homework assignment over the weekend, you're welcome to go to this URL here, which is the official code that is released by the authors of 3D Gaussian Splatting. You can download the code. There are very detailed setup instructions. You can follow those instructions. You probably need a GPU in order to train this. You can also try it on a CPU. It might take a little longer, but you can take this code and try to first of all take their data set and see if you can train the model on their data set. But then eventually, if some of you took your own pictures the other day, right? So if you have your own pictures, you can actually reconstruct your own Gaussian splats. But first, you have to run this through this software package called Colmap, which gives you good initializations for 3D Gaussian splatting. Okay, and then you take this, give it as input to the previous method, and hopefully, if everything goes right, you should be able to view your 3D Gaussian splat. Right? So I think this is a good weekend exercise if you want to get your hands dirty on it. Okay, with that, we're going to conclude. I'm sorry I took a little bit longer, but in the next lecture, we're going to talk about applications of 3D Gaussian splatting and Radiance Fields. Right? Thank you. Happy to take questions.
So initially you mentioned like if we are generating the splat points by one map, it will be up to a scale. So how does it change like storing of splat points?
Yeah, it turns out the scale doesn't really matter as long as you get a reconstruction that looks good. You don't really care about the scale. I mean, you don't care if the shoe is this size or this size, right? So that doesn't really matter too much in your reconstruction.
Also, like if we are generating points by motion, then like let's say there is a wall, so we get the corners, but like points on the center of wall won't be taken up by the as key points. So in that case, shouldn't we use them like find a way to get those points as initialization also?
Sorry, what points? I didn't quite
Like
follow
if
that.
we are generating points by structure from motion, so the key points will generally be corner points or like points where the gradient is large.
Right.
So like if center of wall.
Oh, I see. Yeah. So what happens is that the splitting strategy and cloning strategy that we talked about takes care of that. Right?
But if it's a large wall, then it would take a lot of.
Yeah, but during the optimization process, you do that fine, right? So you just keep splitting the Gaussians over and over again, and you will then have enough Gaussians to model the whole thing. And also, if you have walls that don't have a lot of features, like this one, right? You also don't need a lot of Gaussians to model it. You could model this entire white surface with just one very flat Gaussian, right? So that's the other thing as well.
What happens to the high frequency part? So how accurately Gaussians model?
Yeah, so it turns out that with 3D Gaussian splatting, you just add a lot of Gaussians. So even if you have high frequency parts, because you have millions of Gaussians, it's able to capture this quite well. Like we saw in this example, right? Like if you see this example, there's lots of high frequency detail, right? So you see all these threads and so on and so forth, right? If you zoom in close enough, you will see lots of tiny little Gaussians there, right? Yeah. So you see all these Gaussians here, like this, like this, like this, right? So it turns out that if you just add enough Gaussians, you can capture the whole thing.
So but why there is no background in this image? Like when we give, is there any processing that?
Yeah, they probably segmented out the background to make it easier. Yeah. Because you're viewing this on Amazon, you don't want to see the background.
So the Gaussians are very sparse and discrete, right? And this shoes is looking like very continuous surface. How exactly is that?
The Gaussians are sparse relative to like NERF, where you would have to sample the whole thing very densely, but they're still millions of Gaussians, right? Like think about like images, right? Pixels are sparse. Well, they're there's only so many pixels in an image, right? It's the same thing here. Maybe your image has 1 million pixels, right? You have 1 million Gaussians here. So in an image you see details. You see details here as well. Right? So it all goes down to like what is your basis function? Like if you want to look at it from a signal processing perspective, right? So this complicated signal that is the image is a combination of lots of simple signals, right? You just have a lot of those signals, and therefore you see the image.
So the SFM gives the means up to a scale.
Yeah.
Yeah. So when we optimize for the means here, so how is it changing? Will it be up to scale?
It doesn't matter. Like the scale factor is just one scalar value that you can multiply with everything, right? So if you're doing it in meters units, or if you're doing it in centimeter units, if you're doing it in some other units, it doesn't really matter. Right? So SFM gives you some unit.
Some random.
You don't know what that unit is. You don't know if it's meter, and for that you need that scale factor. But if you don't care about the unit, here we are only looking at the images. We don't care about whether or not this is metrically correct, right? So then it doesn't matter. Yeah.
Is the segmentation, so this object doesn't have background, right? Is the segmentation done before the Kolmar procedure?
Good question. I don't know about this particular case, but you can do it either way. Right?
Like even after the model is formed?
You probably want to do it after you segment because, yeah, if you don't segment, then you get points that are in the background that you won't use for optimization. So I think, you probably want to use the same data for both Colmap as well as the Gaussian splat.
If I want, like I have images with this object, right? But I want only the model of the shoe. Is it better to segment it before the Colmap procedure, or is it better to segment like after we have a 3D Gaussian model?
I would segment it. I see. Okay. I think you probably just want to segment it first, and then do Colmap and then 3DGS.
So the contribution is 3D Gaussian as well as having a rasterization algorithm is their key contribution.
Correct. Yeah. Efficient rasterization.
And in the church scene, the sky was all black, right?
Yeah, probably because they don't have cameras looking at the sky. Yeah.
So regarding the rasterization part, so basically, is that equivalent to we are projecting this 3D Gaussian function onto the edge plane, and because Gaussian, Gaussian has nice properties, once they are projected, they will have.
Right. Rasterization is Gaussian projection plus blending. Blending. Yeah, because projection simply means you're projecting something, but the blending is what gives you the actual color. So rasterization is both together. That we call rasterization.
And so in that equation that you had mentioned earlier, color into alpha I and then product of 1 minus alpha I.
Yeah.
So that 1 minus alpha I is equal to the, so when we project a ray and we have, let's say, n Gaussians in that particular ray, those are those accumulated opacity?
Correct. It's the product of the opacity of all the other Gaussians.
Along that.
Along that ray. So this is a way to blend things.
This is all equivalent to that nerve setting itself.
It's equivalent to that setting, yeah.
So both are trying to get the radiance fields by different methods.
Correct, yeah, you could think of it like that, right? So, I mean, at the end of the day, you're actually getting the pixel values, right? Both are trying to get the pixel values through volumetric rendering. When you do the volumetric rendering, you need to know the radiance. NERF stores it in a neural network, whereas in Gaussian splat, you store it in a Gaussian function.
Very good. Because
so whatever demo you showed for splatting, right, that can't be done for NERF because every time you switch positions, the evaluation of the neural network has to happen.
Correct, yeah. Well, I think these days you have methods that can do it for NERF. Like there's something called instant NGP, but it's slower than Gaussian splats.
Okay.
So you can still do it, but you need a powerful GPU if you want to do it. You can't do it on a browser like how I'm doing it.
So that's why most of the results they show for NERF are offline.
Correct.
They would have generated something and then make a video.
Correct, yeah. Whereas with the Gaussian splat, you can do this, you can view it online. Right? So there's a difference between fitting and viewing. Fitting is still slow with Gaussian splats, but viewing is fast. Right?
Another doubt, how do you actually host these models on websites? Right? Is there a way to do it?
Sorry, force these models? What was the question?
These models hosted on the website, like.
Oh, how is it hosted on the website?
How is it?
I think the way that people distribute these models is just as PLY files. Yeah, that's how they're distributed. So it's PLY with additional parameters that store all the Gaussian properties.
So they just load the model in the browser.
Yeah. So they have, I mean, PLY files, I think, are just lines and lines of XYZ positions. So you can add that with all the other parameters. And if you have a special, you need a special loader. But if you have a special loader, you can do that.
Not a question related to this, but let's say we have PLY files and other parameters. What softwares are used for?
There's a few different viewers. I've lost track of them. I don't know what's the latest one. But I think even Blender can open these things now. Yeah. And there's also like a proprietary format for 3DGS from, I think...
SIBR.
What's that?
SIBR. SIBR, they have mentioned it in Gaussian.
Oh, yeah. But now there is this new format from, what is the company? I'm blacking out on the name of the company, but they're trying to standardize a format for 3D Gaussian splats. Yeah.
Now I've seen practice.
So one question is, this is almost a two-step process, right? Because we have that SFM process.
Yeah.
Is there a way, or are there any papers as such where they have initialized XYZ itself directly and then try to optimize
Yeah. So there's definitely work that tries to do that without using Colmap. They usually tend to be less performant than methods that use Colmap. Colmap is still required, even today. Yeah. Okay.
So I have some doubt related to the dynamic Gaussian splatting. So my thesis is oriented towards that. So
Oh, okay. Maybe we can take this offline. Yeah. Sounds good.
Very useful, Prof. Because from the paper it's difficult to understand.
Okay. Glad this is useful. Yeah, thank you.
Even the nerve paper as well.
Yeah.